and my project is on machine learning and its visual applications. What is machine learning? Well, machine learning are basically the methods by which computers can emulate human intelligence. This is done through the identification of patterns in data in order to apply those patterns to unseen data, similar to how a human learns by making observations, drawing conclusions, and applying those conclusions where applicable in the world around them. Machine learning is useful because it allows us to automate many processes and allows us to perform tasks much more efficiently, such as counting red blood cells or unlocking our phones. My research question for this project was, how does choice of features and classifier affect classification accuracy of the MNIST dataset? And features are basically elements that you can take away from the data. Like, for example, if you have a fire truck, you know that it's red, you know that it has wheels, stuff like that. And for the classifier, it's the method in which you classify whatever your data is based on its features. So if you wanted to classify a fire truck as a fire truck, you would use your eyes and your brain and say that's a fire truck based off of it being red and having wheels and stuff like that. The MNIST dataset is a dataset which contains 70,000 handwritten digits. They are stored as bytes, and they are organized in a training set of 60,000 digits and a testing set of 10,000 digits. The training set is meant to allow the machine learning algorithm to train itself to recognize certain patterns within the data, and the test set is meant to allow the algorithm to test these patterns against unseen data. The training set and the testing set both have labels associated with each digit, but for the training set, the labels will be used within the training so that the machine learning algorithm can make its distinctions. And then the testing set, the labels will be used separately. So the machine learning algorithm will apply its own labels to the testing set, and then we will use the labels that were given to us to test how accurate the machine learning algorithm was. In order to extract features from the data set, we have to first format the data in a way that it can be worked with, which means we have to convert the bytes into color values for the pixels of the images so that we can work with them visually. And then also, I binarized the images to make the data simpler to work with, which basically means that the data came in grayscale and I converted it to black and white. Then for the actual features themselves, we extracted gradients from the data and organized those into a histogram of oriented gradients. Gradients are the derivatives of multivariate functions, and basically multivariate functions are functions that have multiple inputs and outputs, and as a result, if you wanted to look at this function visually, then it would have more than just an x and y axis. And you can really only visually go to where it has a x, y, and z axis, because past that, there's no way to look at the function visually. Gradients are expressed as a vector, which contain the directional derivatives of the function. And basically, the directional derivatives are just the derivatives of the function with respect to a particular variable within the function, since there are multiple variables. And the way that these gradients are expressed in my data is that within these number images, there will be a change from black to white pixels or white to black pixels, and it'll be in a certain direction. So when you would get to the edge of a 0, you're about to hit a white pixel from a black pixel. And basically, these gradients will detect where there is a change from black to white or white to black, or just no change if it goes from black to black or white to white. And these changes are expressed in radians because you can find the angle of a gradient and that'll tell you the direction that the gradient goes in. And depending on the angle, you will be going in a different direction. And the reason that we are using a histogram of oriented gradients is because we can take those gradients that we find in a single image and then organize them into a way that's easy to interpret. So we can take these histograms and then compare them to other histograms of other numbers. Once we retrieve these histograms, we run the data through an SVM. And basically what an SVM does is that it classifies our data by mapping those data points onto a hyperplane. And basically what a hyperplane is a space that has one dimension less than the data you have. So if you had 3-dimensional data, then you would map it onto a 2-dimensional space. So if the data had X, Y, and Z components, you could just map that data onto an X and Y coordinate grid. And basically, the SVM will take that data and draw distinctions between its different classes. And it basically does this with the training set because the training set already has the labels. So all the SVM has to do is just separate the training set by its different classes. And then what it does is that it applies these separations to the testing set, which isn't already separated by its classes. And so the SVM will classify the testing set by applying these separations that it got from the training set to the testing set. So these are the initial histograms that we got for each digit. And as you can see, there are clear differences between certain histograms, like for the histogram for 0 versus the histogram of 1, there's clear differences. But if you take the histogram of 0 and compare it to the histogram of 8, they look fairly similar. And these histograms are basically averages of all the histograms for each digit. So you have the average histogram for 0, the average histogram for 1, and so on. Next, we created a confusion matrix, which shows how many times each number was classified correctly and how many times it was classified as another number. The vertical axis represents predicted classes, and the horizontal axis represents actual classes. Based on this confusion matrix, you can see that 0 was classified as a 0 610 times. 0 was classified as a 1 0 times. 0 was classified as a 2 46 times, and so on. And so as you go to the right, you have 1 was classified as a 0 0 times, 2 was classified as a 0 46 times, and so on. The results of the SVM that we were getting from the initial data that we used was pretty bad. There was an accuracy rate of about 51%. So what I did was that I removed gradients that seemed that weren't in use, because in the previous histogram there were gradients that had no bars. So what I did was remove those, and when I did that, the SVM seemed a lot more efficient at classifying these different digits. And we ended up with an updated confusion matrix, which seemed to have much better classification results. And also our accuracy rate went from 0.51 to 0.7, which was a pretty good increase, but is still a pretty mediocre accuracy rate overall. 0 and 1 were the digits that were most differentiable from each other, with the highest accuracy score being 0.99. This shows us that using the SVM with the histogram of oriented gradients is most likely not the optimal way of classifying the MNIST dataset. I would like to give a thanks to my supervisor, Miss Carolina, for teaching me what I know about machine learning and Python to this point, and Rene Vidal for letting me use his lab.